everybody here?
No, yes.
No.
Good morning. Guys, good morning. We'll start now.
Okay, so good morning, everybody. Yesterday we were talking about state space models, and I went in some detail through this simple example, showed how you formulate the model, how you write down the likelihoods, and how you can sample that using one MCMC method, this random walk metropolis hustings. Next, I just want to make the point that you can do exactly the same thing with much more complex, much more realistic models. We are not going to do it here in the lectures. I mean, it's just the same thing, but it's like technically more demanding. This is just an example where there is like a simulated movement track. This red one, which comes from a bit more complex model. There is some behavioral switching, so this red line shows like the realization in the simulation that whether you were in a resident mode or in a dispersing mode. And then these observations here, they include some GPS error. So in the simulation, you added some location error to the true locations. And then you start just from those simulated observations with the error and try to recover everything, try to figure out what are the parameter values of the model, but also try to figure out what was the true path of the individual. As you see that there is a lot of GPS error. These are the data points that you see when you start the estimation. But after you have fitted the model, you get an idea of what is the true path of the individual. So you see this blue color in the graph. That's like the confidence about where the true locations were. So essentially you do some kind of averaging, so that like even though this is your observation, you don't think that the individual was there. You think the individual was somewhere here, because there is data also from the other side. But you don't do this averaging, but just by taking the average, but through the kind of the likelihood approach. This blue line here is your inference about the behavioral mode of the animal at any given time. So you see that when it was in reality in this residence mode, you estimate that with quite high likelihood it was in that mode, and vice versa. Here we estimate a low likelihood, but this inference is quite noisy. You are not certain because there is so little data. Okay.
What is the yellow point? Circles?
I don't remember. I have to read. Yeah, that might be the resident mode observations. Please.
So actually, if you have several modes, you add more parameters to, for example, to deal with probability that at the right, at the current step or current state, the animal is at this mode or this mode. These probabilities you estimate.
Yes. So if you have, let's say, two modes, then you have the parameters for each of those two modes. So you kind of double the amount of parameters. But in addition, you have switching rates. Yes. So if I'm now in mode 1, what's the probability that in the next time step I'm in mode 2, and vice versa. So you may have two additional parameters just for the switching. But I mean, in more complex models, even the number of modes you have, that might be a random variable. Maybe you don't want to say in advance how many different modes you have.
So what is the posterior ring? Which line? Ask what is the posterior ring?
Oh, in this? Yeah. So here this blue color, that shows the posterior distribution. So the most dense blue, which is this line, is like the posterior mean. And then the contour lines show the distribution around that. Okay. So that shows like your best guess of the true location of the animal plus the confidence around it. Okay. Let's then go talk a little bit about model validation. And I just outlined it here 4 kind of strategies that you can take to model validation. The first one is that you just don't do any model validation. Just trust the model that you fit it. And this kind of sounds silly to do it, but I think if you read the literature, this is still the most common approach, that you just fit the model and then you do some predictions, whatever you do. You don't really do model validation. And this is of course a pretty bad thing to do, because as we know, all models are wrong, and it's not at all clear that the model you are fitting makes any sense. I mean, you can always fit the model to the data, you can write down the likelihood, you get the best estimate, but it might be just completely wrong.
But if you don't have a competing model, what would you do?
I'll next talk about model selection. This is just about validation of if you just work with a single model, but you still want to say somehow if this model is reasonable. Then the second strategy here is that you take all your data, you fit the model to that data, and then you check if the model can reproduce in some sense that same data. Okay? For example, you take this model that you fitted, you simulate the model, and then you somehow compare the simulated data to the real data. This sounds pretty circular, because you are using exactly the same data to fit the model and to validate the model. So do you think this makes any sense? I mean, you are not allowed to answer. We discussed this yesterday with you, but you others, is there any point of doing this? Sorry, I couldn't hear either of you.
To check if your model is working okay. It doesn't say much about if the model is good or not good, but it says if you have a problem with the code.
Oh, if you didn't make a mistake in the programming.
Yeah,
okay. And what was your idea?
Yeah, so it's not exactly a validation of check on the same data. So you can't tell if you take some other data, if the processes are reasonable, because you fit the parameters to this data. So.
Okay, yeah.
I think it's a very good thing, in fact, because it's possible that your best fit of the parameters is actually very, very bad. And the real probability to get the real data is like nothing. So in this case, if you try to simulate the process, you never get your real data back, or nothing similar. But you won't see this, because you just get a number of the likelihood, and if you don't have an intuition, you won't see that this number is actually like really bad.
Mm-hmm.
I guess it's better even to do model selection, but this is also a reasonable thing to do.
I think the answer lies within the interpretation of the word can, which is continuing what Michael said. Can is a question of probability. And in the word probability, can you get the data that you fit it to? Because in any sense, this is circular. Okay, you fitted the data to the model, it's the best likelihood. You got the best likelihood. For certain, you can get the same data. The question is the word probability.
Okay, I think out of these 4 pretty good answers, I maybe mostly agree with Michael, or what's your name? Michael. So even you use the same data, it's not at all guaranteed that the model does a good job in reproducing the data. I mean, let's say that this is like the dispersal distance that you somehow manage to record in for some species, and let's say that it's like highly leptokurtic, that there is like a long tail. Okay. You have observations also for very long dispersal distances, but then you fit something like exponential curve to this data. So what does the best fit look like? I don't know, something like this. Because all exponentials, they go very fast to zero, so you cannot replicate this tail. Okay? So if you fit the model, I mean, you can still fit this model to the data. You will underestimate this tail, but then you will overestimate these short distances, so it tries to make the best possible balance, right? But if you now compare the model predictions to the real data, you see that this tail is missing, okay? And even though we used exactly the same data to fit and to compare, so what you're actually doing in this strategy 2 is to test the structural assumptions of the model, if they are reasonably in line with the data, okay? And this is something that you can always do, because if you have the data to fit the model, then you can compare to the same data. So I think it makes sense to do it.
Can you put this in a general context? Jim Clark of Duke published in 2001 a paper in Science that summarized the ecological forecast, models to forecast ecological dynamics, and one of the main notions in this paper was that uncertainty can be divided into 3 components. One is the inherent uncertainty that is a property of the system, and you cannot, even with perfect data, you cannot resolve, you cannot understand this uncertainty. Then the second is parameter uncertainty, that you know the process, but there's some uncertainty about the parameters that govern this process. And the third is model uncertainty, which means which process produce this pattern that you now observe. So in this sense, what you are actually doing in step 2 is assuming that there's no parameter uncertainty, or is very low parameter uncertainty, and you ask whether the model uncertainty here is big or small, if you really have chosen the right model for this particular process.
Okay, but of course it's even much better if you can compare to independent data. So one way of doing this is that you just split your data to 2 slots. The other one you use to fit the model, and then you predict the other part of the data which you didn't use for fitting, and again in some way you compare if the model can predict that data. So this is called cross-validation. And then the even better thing still to do is that if you have data from like 2 very different situations, let's say that you work with this animal in 2 different populations, for example. So then you fit the model to data collected from one of these situations, and you try to predict this other situation. If your model is able to reproduce the situation 2, then you might think that, okay, it's not only like the structural assumptions are okay, but also the parameter values that you estimated, they are somehow global. They are not only valid in this situation 1, but they can also predict what happens in situation 2. So this example, which I showed in my talk in the first day, where I fitted the data to this landscape, and then I tried to predict how the individuals move in another landscape. That was like an example of this case number 4. Then, I mean, in which way you actually compare the model to the data? There are, of course, huge amount of degrees of freedom there. There are like more numeric approaches. You can look at like deviance, these kind of likelihood-based numbers. But I think it's often really useful to at least additionally look at some politically relevant quantities. I mean, things that you are interested about in your research, you predict those with the model you compare. You use those as statistics to compare the model and the data. because like you said, you know, these numbers, like whatever deviance is like minus 420, is it good or not? It's hard to say. I mean, of course, you have like some ways of assessing that, but if you just plot the data based on the model and then the real data, that often gives you a very good impression of how well the model is working.
I have a question. If you do this, you try to do the model by the first set and then check the second set, and it's not working. You didn't do it well. Can you do it again and try? Statistically, is it okay if you try again and then again check it?
Okay, that's a very good question. So when you do this kind of prediction, what you want to compare are like the statistical properties of the model, not just like a single realization, because you said that there is this process error, this inherent error. If I use the model to do a simulation, even if I use the same parameters, every time I get a different answer. Okay, so you don't just want to compare to one of these answers, you want to compare to all of these answers. That's why, for example, in this case I did 1000 predictions. Okay, so I get like 1000 different answers to which I can compare to. That's why we have these confidence intervals here. They show like the range of model predictions, and that's what you want to compare the data to. Yeah. Actually, what these confidence intervals here include, they include parameter uncertainty, because every time I did a new simulation, I sampled the parameters from the posterior distribution. I'm using different parameters every time. And then they also include the process uncertainty. But they don't include this model uncertainty, because I just fixed the model. I didn't try more than one model.
There's an implicit assumption here that the system should behave the same in these two regions, which is might be untrue. So it could be that the model will not fit the other landscape, not because the model is wrong, but because the system works differently in this other landscape.
Yeah, that's a very good point. So what I'm assuming here is that the system is such that, you know, these butterflies, they only use like local information, so that it's kind of and this classification of the landscape to these habitat types is the relevant classification. Okay, these are my assumptions. So if this is true, then the butterflies, you know, should follow my model, and they should do exactly the same, follow the same rules here and there. And if that's the case, then the model prediction for landscape B should be good. But if any of those assumptions is not true, then of course that shouldn't be the case. So let's say that this model validation exercise shows that I cannot predict what happens in landscape B, but I do a cross-validation in landscape A. So I use half of the data to fit the model, then I predict the rest of the data. Let's say that produces a good result. So what would you conclude in that situation?
The system behaves differently. The other system doesn't obey the same rules. Maybe the habitat definition are not the same. Maybe, I don't know, the population has another genetic component and they behave differently. But that you cannot conclude or interpret the results of your model in a wider context. Yeah, exactly. It would say that, you know, the model is still reasonable because I can reproduce this data, but then something changes when I go there. It's not just the landscape structure that changes, I mean, that I accounted for, but something else changes. The butterflies might be different there because of like a genetic difference, or then the habitat types, as you said, maybe they are not exactly the same. I thought that they are the same, but the butterflies, they don't agree.
Anyway, I think theoretically, perhaps you can use cross-validation, and you can use this prediction method and keep some of the, when you do this, you keep the old parameters, when you do this prediction, you use the same parameters for diffusion rates, behavior at edges in landscape A as in landscape B. Then one of the interesting things that you can do, you can keep just some of them and some parameters to estimate from the new data. And then you can perhaps see whether some of the parameters of landscape A or some are relevant to landscape B.
Yeah, another way of doing that is that you just fit the model separated the data from landscape A and B, and then you compare the parameter estimates.
Imagine that you do the third strategy of cross-validation and you don't find the good fit. So you go back to the model and you try to improve it and so on. Can you then go back again and try to do the cross-validation again and again and again? Is it considered some kind of phishing?
No, that's valid to go on like that. That let's say that the cross-validation shows that the model is not good. But it also has some additional information because you can see somehow in which way the model is not good. And then you can use your biological intuition to figure out like what's probably missing from the model. Okay, you add that, then you repeat the same procedure, and you know, if you now get a good result for the cross-validation, then you are done, and there was no like circular, you know, phishing type problem here.
So looking on this figure, now it seems that the model is very good in predicting in the low range of the distance move, but then the butterflies switch somewhere around 700 or so. They switch to a very different behavior. So now you can reconstruct the model knowing, I don't know, adding a threshold, and then you can significantly improve the results here, no?
So you are saying that the model doesn't fit here?
It's the log scale.
Well,
but not as good as it is.
I mean, this is actually something we discussed was yesterday, that it just looks like that because of the log scale. If you don't use the log scale, then it looks the opposite.
Okay.
I mean, here the observations were 0, 0, 0, 0 for these distance classes, and then the model prediction is that it's definitely 0 here. Here it's on average like 0.1, but 0 is the most likely one. And even here, on average 1, but 0 is very likely. So the model fit is good here as well. It just doesn't look like that because of the log scale. Okay, let's then move to the related issue of model selection. The point of model selection is, of course, that you have a set of competing models, and you want to know what is the best model. So, still kind of the most common option in this respect is that you try only one model and hope that it fits nicely enough. This is actually something that I've been doing in maybe even most of my papers, because for example, when fitting this diffusion model in heterogeneous landscape, it's technically such a tedious thing to do that you don't want to try 10 different models, because after you have done this one single model, you are like, oh, I never want to do that again. And that's the problem with complex models, that often they are so tedious to work with that then you kind of forget about model selection. Okay. Then the second option here is that, basically related to those model validation procedures, is that you just see which model reproduces the data, preferably some independent data, using a summary statistic that you best like is biologically relevant. This is not like a formal model selection procedure, but I think this is something that makes sense. It's like to visualize the models. That you just simulate this, you fit all the competing models, then you generate simulated data with them. You compare some statistic, like whatever distribution of movement distances, which model makes the best job. And then we have an array of more formal model selection methods, like using AIC, BIC, DIC, Bayes factor, and so on. How many of you have been using at least one of these methods? Good. So you know what these, at least roughly what these are about. I'm not an expert at all in model selection, so I'm not going to talk about these methods too much. I'll just say that, unfortunately, like all of these are problematic, especially in complex hierarchical models. So there is no good standard method yet for model selection for hierarchical models. So it's really an active area of development. Like we had recently a kind of a small workshop seminar on model selection where we invited people from mathematics who developed these methods, and the conclusion was that in these hierarchical models just none of these work. For example, Bayes factor, which is really sensitive to the prior assumptions that you make. So their opinion was that this kind of cross-validation exercises are often a good way to do model selection. But still, let me go through one of these, which is the DIC, Deviance Information Criterion, as this is something that you will use in the exercises. I'm not saying that this is like the best of these methods, as they all have their own good and bad sides, but this is something which is really easy to apply in the Bayesian context. So deviance is basically the likelihood of your data. Here you see probability of, did I write this the wrong way around? I think this should be y given theta. Yeah, this should be the probability of observing the data given the parameter. Okay? So this is something that you can calculate. It's the likelihood of the data, which is something that you have to calculate anyway when you fit the model. So the deviance for a given parameter vector is simply you take the logarithm of that and you multiply that by -2, and then in this definition there is like an additional kind of normalizing constant c, which you don't need to compute in practice. I mean, you don't need to care about this c, because in the end we will take the difference between two deviances, so c cancels out. Then you need to figure out what's the expected deviance, which is denoted by d over bar. So here we take the expectation over kind of all possible values of theta using the posterior distribution. I mean, you take the expectation over the posterior distribution, which means in practice that when you do the MCMC, that gives you the sample from the posterior distribution. You calculate the value of deviance for every sample, and then you just take the average of those numbers. That gives you the expected deviance. Then you figure out what's the mean parameter vector, the posterior mean of your parameters, expectation over the posterior. So now you simply take that sample from the posterior and take the mean of that vector over the MCMC iteration rounds.
Because some of the distribution of your expected parameters could be not symmetrical, isn't it better to take the mean instead of the mean? The median instead of the mean?
Well, if you work with DIC, then you take the mean. But I mean, if your distributions are highly unsymmetric, then this is not likely to work as well as in the case of symmetric distributions. But you shouldn't take the median, you should take the mean. Okay, what you then do is that you calculate what's the value of the deviance for this mean parameter value. Okay? Which is like your best guess of the parameters. So this is like the deviance at the kind of the best value, and then this is the mean value of the deviance, where you also account for the little bit worse values, more unlikely values of the parameter vector. Then you take the difference between these two, and for let's say a magical reason that we don't need to go too deep now, this gives you what's called the effective number of parameters of your model. Okay? And then the DIC, the Deviance Information Criterion, is the effective number of parameters plus expected deviance. And this is now your measure of how good this particular model is. Okay? As the idea is that the model, I mean, the smaller DIC, the better. So the model with the smallest DIC is estimated to be the model that would be best predict a replicate data set which has the same structure as that currently observed. This is basically what DIC is trying to do. So as you know, if you add more parameters to a model, the model will always give a better fit, of course. because you can reproduce the same model by setting this new additional parameter to 0. So the idea is that you select the model which fits well the data. That's what the deviance is showing, how well the model fits the data in terms of the likelihood. But then you punish for the number of parameters. If you have many parameters, you need to have a better fit. So let's do this in practice for this simple toy model that I was talking about last time. This correlated random walk model without any observation error. So what you do is first you run your MCMC. Here I've been running the MCMC for 10,000 iteration rounds. We had these 2 parameters of the Weibull distribution and 1 for the von Mises distribution. And after you have done that, you can compute all these quantities that you need for DIC. So this is the code, I mean the full mathematical code that I needed to write to compute these quantities. So it's really easy to do. First we have this expected deviance. So what I'm doing here is to just take this minus 2 times the log likelihood of the data for all the parameter combinations that I sampled from the posterior. And then I just take the mean of that vector. That gives the expected deviance, which is just a number, 499 in this case. Here I put this value C to 0 because, as said, when we compare models, the relative values only matter, so we can put that to 0. Then I computed the mean parameter vector simply by taking the mean of this table of MCMC samples that I collected. Here we have 3 numbers because we have 3 parameters. So this is the posterior mean. And then I calculate the likelihood of this expression to get the d of the mean parameter vector. That gives me the effective number of parameters, this difference, and it turns out to be 2.9 in this model, where in reality we had 3 parameters. So it's somehow, I mean, it makes sense, this number. And then I just sum this number with that number to get the DIC of this particular model. Now if I have another model, I calculate the DIC for that and then I compare. Okay.
So the actual difference in number of the DIC that you get from 2 models doesn't mean something. The actual difference, you get another one which is 488, and then you get 502.
Yeah, I mean the absolute difference tells how much better the model is, and then there is like a threshold above which you can be, confident that it's a better model. You can drop the other one. It's like a likelihood ratio test.
Oh. If you run this model again, these 2 models on another set of data, you can get different results.
Another set of data?
Yes.
Yes, of course. Yes.
So that's why you said there is a threshold that you need to have between the 2 models to say that one is better than the other.
Yes, that's one way of looking at it. Yes.
So if you would got an effective number of 2, so what would you do? You need to remove one parameter, or? Yeah,
it might be that you formulate the model in such a way that two parameters you can distinguish them in the model, that it's over parameterized. So you should see that in the effective number of parameters. I mean, of course, in this case, what's the number of parameters, so you can pretty much substitute that for this. But in a hierarchical model, if you have a random effect model, you can have a case where you have 100 data points, but you have 200 parameters. I mean, without this kind of hierarchical structure, it doesn't make any sense because you can't fit such models. But in a hierarchical model, that's equal. I mean, that's absolutely valid. We fit those kind of models all the time. That we have more parameters than data. But then the effective number of parameters is something very different from the true number of parameters.
But in a way, the number of parameters is derived from the Deviance.
Yeah.
Everything in the DIC is derived from the Deviance. There's no really, and it depends on the uncertainty in the data, not really on the number of parameters.
Okay, that's a bit too deep question to answer right now. I have to also explore better the literature to be really able to answer that question. But you are right that everything is derived from the deviance. But I think like the point estimate for this effective number of parameters, I mean, should be pretty much independent of the size of the data. Of course, you are more certain about that when you have more data. Maybe there is somebody in the audience who knows better. As said, this is not really my core area.
Say something about AIC. The AIC basically you calculate the number of parameters computing AIC, but actually it's not the number of parameters. It's the trace of the influence matrix. It's trace of the influence matrix, which is never mind the method to calculate from the data. It turned out to be the number of parameters. You don't know that. You simply calculate the number of parameters. This is not what you basically need to calculate. I mean, the theory of AIC does not relate anything to number of parameters, but to the trace of the influence matrix, for example. So maybe, I don't know anything about DIC, but maybe it's sort of the same here. It turned out to be the number of parameters, but here it does. I don't know.
Okay, in the exercises you are fitting these different models. Exercise 1, 2, 3 is basically model 1, 2, 3 and so on. So what you will be doing there in the end is to work out the DIC of these different combinations. If the true data comes from model 1, if you simulate data with model 1, then you fit model 1, 2 or 3 to that data. You compare the DICs. So then you will see how this works in practice. Okay, so now I'm in the end of my talk from yesterday. Just the conclusions. To remind you that the idea of state space models is that they combine a process model with an observation model, and they provide a very general framework for formulating and fitting movement models, also other kinds of models. You can visualize these state space models using a directed acyclic graph, DAG, which is a very useful way to illustrate how the components of the model link to each other. These models allow you to bring some biological knowledge into statistical inference and give you a mean to work with, for example, data with missing observations, because a missing observation is like a hidden state. You can consider that as a parameter of your model. Unfortunately, fitting these models can be technically challenging. I mean, not always, but in some cases it's like an active area of research. How do you actually fit these models? And there is a great number of methods. Most are essentially variants of the MC-MC methods that we discussed in this lecture. All models are wrong. Some still might be useful, so you should take model selection and validation seriously. Any questions about these issues before we move to today?
How do you account for the different sensitivity parameters? Is it inherent in the MC-MC that some parameters can have much influence relatively to the others?
Well, that's part of the parameter estimation scheme, in the sense that if one parameter, like a small change in one parameter, changes a lot the outcome of the model, then of course you are likely to get narrow confidence intervals for that parameter. But then another part of your question is that after you have fitted the model, let's say that you want to do some scenario simulations. You want to ask that, how about if this parameter changes, how does the model outcome change? Okay, this is not, of course, part of the fitting procedure. This is what comes after that. And in that case, it's often difficult to think, I mean, how big changes you should try to parameter A versus parameter B, because that's kind of a, for example, a management question, that if I do habitat restoration versus I do something else, how much can I actually, you know, improve like the fertility of the or fecundity of the individuals versus how much can I, you know, lower their mortality. These are difficult things to figure out. You need another experiment to measure those. Okay, so next I'm going to talk about movement models in heterogeneous space. Do you want to have a short break before we go to that? If you want to have a break, raise your hand up. There was a feedback. You raise your hand up, then there is a wave of hands coming up. Okay, 10-minute break. We continue 9:30.